let's review again the CUDA programming model aspect of these things. So from the CUDA programmer's point of view, there's a device memory space. Okay, and then we have seen this slide in a previous lecture. So this is the abstract view of what the programs have access to. So each thread can read, write a per thread register. Okay, and this is the programming view. I'm going to show you in the hardware view. It's not exactly that way. Okay, but there's some implications to that. And you can rewrite per thread local memory, and you avoid that at all costs. Remember, that thing is actually in DRAM. It's very, very slow. So whenever you find yourself in local memory, your performance is not going to be very good. Rewrite per block shared memory, and this is a fast memory, and this is how all the threads in a block cooperate. Okay, and they share data that way, exchange data. In fact, there is a little bit of an ambiguity when we say shared, because shared can be shared in many ways. What we really should say is exchange. This is the memory where all the threads in a block exchange data. Okay. So then there's a per grid. All the threads in the grid across all the blocks can access global memory. And this global memory, once you terminate the kernel, the global memory will settle. Okay, so when you invoke the kernel, another kernel in the future, the global memory will reflect all the changes made by the previous kernel. It's a natural synchronization point. And it's read-only per grid texture memory. So this texture memory actually has some interesting characteristics. And hopefully we'll have time to talk about it, but I'm not going to talk about it. I'll try not to talk about it in detail those 10 lectures where we're going to equip you with all the high-performance programming skills. But we'll probably talk about it in a couple of the case studies that give you additional sort of experience and insight into how people build real applications on this kind of chip. And texture memory is actually interesting for certain types of applications. So the host can read, write global, constant, and texture memory. And so that's the programmer CUDA programming model view. Just the important things that we're going to talk about today is there's a thread. Oh, I should have changed this thing to register. So that each thread can access registers. Okay, and these registers, when assigned to a thread, is really just private to that thread. And no other threads can peek into the register. Okay? And within the block, the access is mostly to shared memory in the sense that it's very fast, it's a local scratch pad, and it's also very convenient data exchange mechanism within the block. Within the grid, all of these blocks are going to be accessed. All the blocks within the grid will access global memory. And then before you go to the next grid, the global memory will settle and be consistent again. And then the grid 1 can see all the data from grid 0. So that's global memory. So let's look at the hardware overview here. So this picture shows the hierarchical picture where at the highest level you have the texture processor cluster, and each texture processor cluster expands into 2 SAMs and one texture unit, and then each SM expands into a more detailed design where you have a common instruction fetch, a shared memory that can be accessed by all the cores, and then all the processors plus the super function unit. So we are going to be talking about shared memory. We're also going to be talking about registers that are actually located within each streaming processor. Okay, we're going to focus on these two. And if time permits, we're going to actually talk a little bit about data cache, L1. Okay, but it's not clear to me that we'll get to that point. So this is a similar picture to yesterday, but the title has been changed to SAM memory architecture, and the text has changed. So the picture is meant to remind you that, still the assignment unit of threads into SAMs will be blocks, right? Whole blocks get assigned to these SAMs. Okay, so that's still a very important thing to remember. So all the threads in a block share data and results in the shared memory, and they synchronize at the barrier sync. And there's a per block shared memory allocation. So this is kind of an interesting thing. That is, you can have a shared resource, but the shared resource will be dynamically partitioned, okay, between units or between entities. Once you partition it, each unit can only access its own partition. But the whole thing can be still shared, right? In that sense, you just push the boundary back and forth. That's a sharing, right? So that is not exactly what the reason why they, name the shared memory. When they name shared memory, they really mean that this is a piece of memory that you can exchange data. That is, even after a partition, I can still kind of creep over to his side and then they'll pick up his pencil, okay? And remember in elementary school, when you sit next to, to this kid, you accidentally cross the boundary and then you get a whack, right? So that's partition, not exchange, okay? But if you have a very good friend, you can just reach into each other's desk space and, get a pencil and an eraser and so on. That's exchange. It's a register file in a SAM. So this is a picture of the SAM. And the register file contains 32 KB of data. Fairly large register file. Okay? Essentially, it translates into 8,192 single precision 4-byte registers. Okay? So you have 8,192 of those registers available. How many registers do you think is available in x86? How many of you know? Okay, quite a few, 8. Okay, 8 registers per process. Okay, the CPU defines 8 general purpose registers. So this is about 1,000 times more. Okay, and it's not because Intel doesn't know how to build large register files. In fact, Intel knows exactly how to build these large register files. If you look at the processor implementation, there's something called register renaming, and those 8 registers gets translated into a huge number of registers, thousands. However, remember x86 has been around for a long, long time, ever since 8088, 8086, 186, 286, 386, 486, Pentium, Opteron, and all that. So in the very early days, in a humble beginning, those things are very, very small, and they wanted to have very small number of registers. And then with compatibility, people needed to keep all these things compatible with the previous instruction format and so on, so it's very hard to increase the number of registers visible to the programmers. This thing is also similar. In fact, if you look at the design, and I'm going to go over that, the number of registers is not even visible to the programmers. Okay? It's an implementation decision. And this is something that can be changed in the architecture moving forward. And none of the CUDA programs should need any change. And this is a lesson that they learned from the Intel history. Okay, so the register file can provide 4 operands per clock to each thread. Okay, so that's a lot of operands per, it's 8 times 4, that's 32 operands per clock, right? So naturally, this is not implemented as a huge, huge structure with 32 sets of wires coming out of the register file. That's just way too big. So this is actually implemented as private register files for each, for each SP. And there are wiring between these things so that just in case you need to reach to someone else's SP register file, and you can do it. In general, that's not because you need to do that on a cross-access basis. Oftentimes it's because you ended up running fewer threads, but each thread needed more registers. So that's why you're going to have to reach into another SP's register file. The text pipe can also read-write register file. So remember that text unit is shared between the two SMs. So the text unit needs to be able to reach into these register files and get operands. Okay, it's a slower process, but it can be done. The load store pipe can also read-write, a register file. The memory accesses will have to deliver all these results into the register file. Let's go over how the register file actually gets used. And you actually don't need to really know this in order to write a CUDA program because the compiler does it all for you. Okay? And you really don't need to manipulate this. However, you actually need to look over the compiler's shoulder and then just see how many registers end up being used so that you can have some performance insight. Okay, so this is what it's meant to be. So as I mentioned, there are 8,192 registers in each SM, and this is an implementation decision, not part of CUDA. In the future, you could easily have double the register file size or half the register file size. More likely the former than the latter. Okay. Registers are dynamically partitioned across all the blocks assigned to the SM. So depending on how many blocks are assigned to each SM, each block will get its share, okay? And all the blocks will receive the same amount because they all come from the same code. They all need the same number, okay? The code determines how many registers each thread will need. So all the blocks will essentially require the same number of registers. Once assigned to a block, the register is not accessed by threads in other blocks, okay? So it's a dynamic partition. You go and say, I need so many registers. The hardware will give you that partition. And once the partition is given to you, no other blocks can access this particular set. Okay? And each thread in the same block only accesses registers assigned to itself. So you will have, let's say, 256 threads in a block. So every register, every thread will have its own little partition in the register file, and nobody else will be accessing that register. So in your matrix multiplication, you probably had that experience. When I gave you that piece of code, I said, okay, load the two input arrays. Okay, load the two input arrays into the shared memory, right? But you're using a local variable to hold that temporary result, right? So you would, for each thread, you will go over pairs of tiles. And after you finish each pair of tiles, you will generate 256 of those temporary results. But if you look at the thread code, that result, that temporary result, every temporary result of every thread is actually in a local variable. It's not in an array anywhere because it's being preserved in the register. So you're literally saving 256 of those temporary results in the register file in a matrix multiplication. When you have 3 blocks running in the SM, you're actually saving 768 of those temporary results, all in the register file, throughout the matrix multiplication. This is something that most of the CPUs don't do. Most of the CPUs don't keep their registers that long, keep so many results in the register file. Okay, so this is part of the benefit of having a large partitionable register file. In many cases, you end up having some very substantial entire data structure distributed in the register file. and you're accessing them without even knowing. Okay, so that's the benefit of this kind of design. So if you think about it and how these things are partitioned, let's say the 8,000 worth of registers, you can have 4 blocks assigned into the same. So each one will have access to 1/4 of those registers. The detailed partition pattern or policy and so on is not known, and in fact you should not know, because as a programmer it really doesn't matter. In the hardware, the partition could be green, yellow, blue, red, green, yellow, blue, red, green, yellow, blue, red, or it could be all green for a long time, all yellow for a long time. It doesn't matter. Your code will run exactly the same way. Okay? And in fact, there is a partition pattern that makes the hardware design easier. And I assume that that's the way they designed it, because these are clever engineers. But you don't need to know as programmers. It's all taken care of for you. If you have a 3-block situation, then you will have, you can partition the register file into 3 parts. But 8,192 is not exactly a multiple of 3. So you're going to have some change. So the change is likely going to be, distributed in places, but you don't care. Okay? The only reason why you care is there may be situations where if you do the 4 partition rather than 3 partition, you end up using the registers more efficiently, and you ended up being able to get more parallelism going. Okay? And that's a very intricate situation, and I assume that most of you will not run into that situation, but a couple of the groups did run into that situation in the past. Okay, so let me take you through a calculation to show you, how some of these situations could arise. So let's go back to that matrix multiplication example. I have a bad feeling that by the end of the semester, if someone asks you, hey, I heard about this woman Hu and David Kirk class, and you took that class for a whole semester. What did you learn? And I'm really afraid that half of you will say, oh, I learned to write matrix multiplication. Okay. And that would be really bad. Okay, that would really damage our reputation. Okay, so matrix multiplication is really meant for an example. It is simple enough, it's rich enough to illustrate a lot of these things. But I really hope that by the end of the semester, you don't tell people that you learn how to write matrix multiplication, right? You learn how to do massively parallel programming, and you learn how to, develop applications on these things. So, for matrix multiplication here, let's say if the block has 16 by 16, remember we went through that at the end of the lecture last time, 16 by 16 is good as far as the threading hardware is concerned, right? So let's say, we ended up doing 16 by 16 threads. And each thread uses 10 registers. Why do you use 10 registers? Well, if you think about it from the threading code, you will have loop variable, right? You need to keep track of the iteration when you go through that tile, right? The dot product. You need to have, temporary variable for loading from the shared memory. You need to have A and N and M, right? So, 2 local variables. You need to have, a few other things, such as, you're keeping the temporary sum in that thing, right? So when you add them up, you also need to have pointers into the local memory so that you can access shared memory, so that you can access shared memory with indexing, right? So all these things add up. 10 registers go fast, okay? But 10 registers can also be quite sufficient for a lot of the computation, if you think about it, because most of these computations may not require a whole lot of these temporary variables. It depends on the amount of parallelism you want, and I'm going to actually go over that point later on. So let's say you end up using 10 registers. Then the question is, how many threads can run on each SM? So, if you see this thing in the exam, okay, am I making myself clear? So if you see these things in the exam, this is how you could easily do this. Each block requires 10 times 256. 256 threads, each thread uses 10 registers. Okay, so you need to have 2,560 registers. this is one of those things that I always had problem with when I first started working on the course. You know, I came from a CPU perspective, and I have been building compilers and, you know, building hardware for CPUs for a long, long time, right? And I don't deal with 2,000 registers all the time, okay? So every time I start to do this, I need to twist my brain a little bit so that I can actually deal with the numbers right. And it's really, really annoying because, you know what, my brain somehow just always works against me. So for those of you who are from science disciplines, you know, from other science like chemistry or physics or something, you have a huge advantage over me because you don't have your brain working against you, right? You know, every time I do these calculations, my brain keeps telling me something is wrong with that number because when I work on the CPU domain, if I come up with this kind of number, it was wrong, right? And, you know, I was trained to tell that it's wrong. Okay, so 2,560 registers. And, you know, so if you look at the total, 8,192, it's really 3 times this number plus some change. I don't think I need to calculate that change for you, right? I'll be insulting your intelligence. So, you know what? Change, by definition, doesn't buy you what you want. Okay, change is in the pocket. Okay, so what you want is that 3. So you have 3 times the requirement of registers, right? So from a register point of view, you can actually have 3 blocks assigned to each SN and running in parallel. Because we truly have all the 8,192 registers, that's why all the threads in those 3 blocks can truly run in parallel. There's no context switching going on, okay? There's no, you know, hardware going back and forth, moving information between register file and memory, and, you know, in CPU world we call context switching, to be able to run these things in parallel. It's really just everything is there. It's a matter of just getting to the right partition, okay? Now, how about if each thread increases the use of register by 1, okay? What's so bad about using just 1 more register? Okay, it could be bad. Okay, just 1 more, right? You know, just 1 more time, right? Just 1 more, right? If you use 1 more, each block now requires 11. You multiply 11 by 256, you get 2,816 registers. Now, if you look at it, 2,816 times 3 is actually more than 8,192. What that means is you no longer have the same purchasing power. You can no longer purchase 3 blocks. You can only purchase 2. Okay? You are now 2 times 2,816 plus change, even though that change is pretty big. Okay? But it's just not good enough for you to get on right. Do you remember how many of you went to Disney World when you were, let's say, you know, about 8 or 7 years old, and they have these these measures outside the rides, right? And you know, it says 42 inches, right? And you go up there, you kind of tippy-toe a little bit, and you know, you're just 1 centimeter short, right? And then there's always going to be this, you know, very stern-looking, you know, uptight person next to that measure, shaking her head and say, "Next year, remember that?" Okay, you have grown all the way to 41.5 inches, and you know, tippy-toe a little bit, you know, so you're just less than 1 centimeter short. And guess what? Your brother and sister went on the ride, and you did not. Okay, that's essentially what this is. Okay, just 1 register, right? Okay, so only 2 blocks have run on the SN, and suddenly you have 1/3 reduction. One of the kids in your family is now crying, and the other 2 are, you know, enjoying that ride. Okay, and that's really what it is. And you lost 1/3 of your parallelism. Is this good or bad? Depends. Just like in real world, maybe you got some opportunity to build your character, right? So, you know, not getting on that ride may be beneficial for grad school. You never know. So there are also benefits in this kind of stuff. Okay? So the benefit of this kind of stuff is that the dynamic partitioning actually gives you more flexibility for the compilers and programmers. You can oftentimes change your algorithm, and that will lead into more use of local variables and more registers. Or the compiler can sometimes do some code transformation, which will require more registers, but can give you some other benefits, such as efficiency or instruction level parallelism. I'm going to give you one example. So one can run a smaller number of threads that require many registers each, or a large number of threads that require few registers each. And this helps to make this parallel machine more flexible. Okay, so you can run different applications. Sometimes these applications have kernels that require a lot of registers. But you can run fewer of them, but you can still run them. You can run them even, in some cases, even efficiently. And when you have these kernels, big kernels that require a lot of registers, oftentimes you have enough parallelism within the kernel that you may not need to run as many of them to get the peak performance anyway. And I'm going to illustrate how that works. Or you can have very small kernels. Each thread will require very few registers and have very little parallelism within. But this way, you have lots and lots of registers. You can run lots and lots of small kernels. And that gives you finer grained threading parallelism. So this allows you to adjust the granularity of your parallelism and cover a wider range of applications. So from design point of view, this is actually not a bad design. This is probably a more flexible design than most of the CPU-style designs when it comes to running these different styles of parallel programs. Okay, so that's not bad. The compiler can trade off between instruction-level parallelism and thread-level parallelism. But this is a very important thing. It turns out it can have very major performance effects. If you think about this, you say, okay, what would be a good example of the amount of instruction-level parallelism that I can vary by using more registers or less registers? A typical example is that, let's say, if you need to add 4 numbers together, okay, let's say, in your mind, think about 4 numbers that you need to add. This is probably the simplest example we can come up with. So what I can do is I can add up the first 2 numbers. So far, so good. And then I can add one more number to that number. I can add one more number to that number. So I only need to have one temporary result. I just keep accumulating into that variable. Right? I use few registers, 1 in this case, but I need to do this in 3 steps, sequential steps. I cannot do the second step until the first sum is ready. I cannot do the third step until the second sum is ready. Fine? I could also do that by adding 2 pairs of numbers, okay, in that first step. But now I need to have 2 registers, right? And then I can add them together. Suddenly I can do it in 1 fewer step, and I can have more parallelism. But I need to have 1 more register. Okay? Compilers do this all the time. It's called tree height reduction. And there's other similar transformations that we do all the time that require different amount of registers and give you different amount of parallelism. And this is how I actually built my career for about 10 years in the 1990s. I actually implemented a bunch of these kind of things in the presence of conditional branch and so on for superscalar and VRW processors. So those things are very well known and very widely available in commercial compilers today. Now, how does that really work in this kind of machine? It turns out that you can do it the following way. This is actually not a sort of an uncommon scenario. Obviously, it's contrived to in a simple way so that you could get the intuition, but the essence actually happens in a lot of these applications. So you assume that the kernel has 256 thread blocks. Again, that red matrix multiplication example. and 4 independent instructions for each global memory load in the thread program. So what could be happening here, going back to the matrix multiplication example, is that, let's say, I'm going to do one load, okay, and then into a register, okay, and I'm going to do another load into a register, okay. So this uses 2 registers, and then I multiply them together, and I accumulate into the sum, which is a 3rd register. Good so far? I could also transform the code into a more parallel form. I could say, I'm going to load 2 values into 2 registers, but I'm not going to do multiplication right away. I'm going to go ahead and do another 2 loads into the next 2 registers. Okay? And so I will, after those 2, I will do the multiplication of the first pair. So before I go into the loop, I will load 2 values. And in the loop, I will actually load 2 values, but do multiplication based on the previous load. So I will have a kind of a pipeline going in the loop. But that will require me to use 2 more registers. Okay? So these things can actually change the amount of parallelism. Why is the amount of parallelism good? Because as far as the first 2 loads are concerned, there will be additional independent instructions, meaning 2 loads for the second multiplication, followed by the multiplication. So you just increase the number of independent instructions you can use in the thread, okay, after that load. Now, so, if I use, if I have 4 independent instructions for each global memory load in the thread program, and each thread uses 10 registers, global loads take, 2 loads take 200 cycles. Then I can use 3 blocks. And this was just a previous calculation, right? I just calculated it. 256 times 10, and it's, less, times 3 is less than 8,192. Boom, 3 blocks. However, if the compiler can use 1 more register to change the dependence pattern, or even 2 more registers in this case, I think you'll get the same result. So that 8 independent instructions exist in each global memory load. Okay? So just like the example I showed you, you ended up having twice the number of independent instructions that you can have, in between these global loads, right? So then only 2 can run on each SM. I already calculated that for you, right? So, after you use 1 more register, you can no longer run 2 blocks. 3 blocks, you can only run 2 blocks. So that sounds bad. However, because now you have 8 independent instructions, you can, and each one will take 4 cycles to go through the dispatch, right? Remember that? So each thread will now have 32, can tolerate 32 cycles worth, okay? And now you only need to have 7 warps in order to tolerate that memory latency, okay? Rather than the 13 that we had before. So the 7 warps is actually less than the 16 warps that you will have available for the 2, from the 2 blocks. So this may even just be sufficient to tolerate all the memory latency and fully utilize all the function units. Okay? And you actually require half of the warps that you would need in the 11 register case in order to fully utilize your resources. Even though on the surface you lost 1/3 of your simultaneously running warps. Remember, the end goal is not to have many warps. The end goal is to fully utilize all the 8 SPs. If you really need to have a lot fewer warps in order to fully utilize SPs, you can be fine, even though you lost some of the warps. Okay? So if you keep that straight, then you start to build a real intuition on programming this machine. Okay? So that's why, in some cases, you can actually end up with higher performance with, even though you lost 1/3 of your work or 1/4 of your work. So this is the tricky part of compiler optimization for these machines. It turns out that the decision process of making the compiler code transformation in order to get more independent instructions has to take into account the global picture of how many works will be running, unfortunately. And it's actually not something that the production compilers or commercial compilers can currently do. And that's part of what Illinois and NVIDIA are collaborating on. We're trying to reach the point where we can control these things in a more global way. And that's a new generation of technology. So right now it's actually done in a somewhat less optimal way, but it's already doing a pretty good job. So now let's go into constants. Okay. So if you declare a variable in a constant memory, that this variable, this constant, will appear in the same way to all the threads in your kernel. Okay? So all the threads will be using that same constant. So if you have, let's say a physics constant that will be used by all the threads in calculating the force or something, right? And that will be a prime example for using constant memory. And if you have an image reconstruction algorithm and you have some kind of constant in your trigonometry function, and those are the prime examples. Or even if you may even have a situation where a piece of input data is actually used in the same way by all the threads. Okay? It may even be generated by a previous phase of your computing. But as long as it appears in the same way and not changed by the kernel, you can use it in the constant memory. So what happens is that the constant memory is actually cached in the level 1 data cache. Remember, we saw that L1 data, L1 instruction cache. This is what it is. So you actually have a per SN cache, okay, that can actually contain these constants. The first time you use this constant, it may take a long time. But after that, you're golden, okay? And this constant cache is actually broadcast to all the warps. Remember, these warps are executing exactly the same instruction. So if one of them needs a constant value, all of them need that same constant value. So this allows a very efficient implementation of that cache. The cache only needs to have one port. At every clock cycle, that port will provide you with one value. But the hardware knows that if the value comes out, that value will be used by all the 8. Okay? So the implementation is extremely efficient. So this is a very efficient way of accessing values that are common to all the threads in a block. I would predict about 1/3 to 1/2 of your projects will end up using the constant memory. The constant memory cache is limited. So there are some rare occasions where you may overflow the constant cache. But it doesn't really happen very often, because if you look at these kernels, you typically will have a limited number of constant values. But if you end up with a huge formula with lots and lots of constants, you may run into a situation where you may actually run out of constant cache. Okay? Whenever that happens, it could be bad. If that happens, come and talk to me. Okay? You may need to sign NDA, but there may be ways to deal with it. Okay? There may be ways. Okay, so now we're into probably the most important part of the memory model, which is the shared memory. Maybe second most important one. The registers are actually the first order effect that you really need to understand. And I have not told you how to actually figure out how many registers your program is using. But as soon as I talk about PDX code, you will see. Okay. So each SAM has 16 bytes of shared memory. Okay? Interesting, isn't it? The shared memory is smaller than the register file. It's not something that happens very often. So, because this is not a per SP implementation, this is actually a big structure. So you need to get all these ports and all that stuff into this stuff. And I'm going to show you how the multiple access ports are implemented. It's actually banked. So it's 16 banks of 32-bit words. Okay, and you can divide it. So each bank will have 1K bytes, or essentially, I think it's essentially 1K bytes. And if you divide it by 4 bytes, you will get 256 words. So each bank will have 256 words of storage. Okay. So CUDA uses shared memory as shared storage visible to all the threads in a thread block. So theoretically, every thread in a thread block can access anywhere in the shared memory. Okay, so if you write a PTX code, that's exactly what you're going to see. However, that's not very good for your own good. If you have 3 thread blocks running in the SM, then each one will have a partition of the shared memory. And each thread block should only access within that partition. If you access across the partitions, there's a bug in your code. Okay? And do not try to take advantage of that. There was someone in the previous semester who tried to take advantage of that got burned badly. Because you cannot assume that these blocks will always be assigned the same way. Sooner or later you will be burned. Okay? Not used explicitly for pixel shader programs. And this is just a side comment. This is actually something that the GPU, the graphics personality of the GPU, does not use, but the compute engine uses. Usually, these things are designed for the graphics mode, and then kind of changed a little bit, or just kind of made available to the CPU, because that GPU is where the business is. However, for this particular structure, is really added for the compute engine, and is not used by the GPU shaders, because shaders pixels shouldn't be talking to each other. Okay, pixels should be like students taking exams. Okay, they should be just working on their own information. Once they start to exchange information, things can get bad really quickly. This is a review slide of your matrix multiplication code that you should be working on this week as we speak. Okay, so hopefully this will help a little bit. One block computes one square, right? And then so each thread will be calculating one result data point, and so you will be loading a pair of tiles into the shared memory. But you're going to only use a pair at a time. So next time, when you go to the next tile, you will overwrite the previous tile in the shared memory. So you never need to have more than a pair worth of shared memory, in your execution in the current in the block. So let's do a little bit of calculation. Each block requires 2. A pair, right? 2 times width square, right? 16 by 16 in this case, right? Times 4 bytes. So each block will require essentially 2K bytes. Okay? So this is a kind of a nice example where shared memory is actually not a bottleneck. Remember, from threading point of view, we're only able to get 3 blocks into the SM anyway. So from shared memory point of view, you can actually have up to 8 blocks. So shared memory is definitely not a bottleneck here. That also gives you a little bit of hint. It turns out that you can actually have a better algorithm. Even though you're doing tiled algorithm, you can actually do something about, maybe even, doing a little bit look ahead. Okay, you could be loading the next tile while you're calculating the current tile. Okay, and that will double your shared memory usage. But do you care? You don't, because that will double the usage to 6, right? And you can still accommodate, right? So this gives you room for algorithm level, transformations. There are all kinds of clever things you can do. Since each SM has only taken 768 threads, each SM can only take 3 blocks anyway, so it's not a bottleneck.